Hello, and welcome to MongoDB Live and our talk, Kubernetes MongoDB and MongoDB Data Platform. My name is Andrei Belik. I'm a Senior Product Manager at MongoDB Cloud. So in this session, we're going to talk about MongoDB Data Platform and specifically about on-premise and Kubernetes. We'll dive into MongoDB Kubernetes architecture. We'll discuss what's actually happening in MongoDB Live this week and what kind of announcement we made, as well as we'll dive into the best practices of running MongoDB Data Platform and generally stateful applications in Kubernetes. And then we'll talk about roadmap. I am a PM after all. So quick forward. First of all, if you join this talk, I don't need to convince you that Kubernetes is the most popular orchestration platform currently in the world. However, here's the graph for MongoDB, so for CNCF survey from last year, and it was updated this year as well. When you can see that container adoption within the development and test has been very, very strong over the last 5 to 6 years. Over the last couple of years, containers really started to take off in production. And we can see the same with our customers. More and more of our customers asking us for our story around running MongoDB and persistence services from within Kubernetes. So let's quickly talk about MongoDB, as a couple of key concepts will be relevant in this conversation. First of all, our key MongoDB cluster is replica set. It essentially consists of a number of nodes between 2 and 50, and each node has its own copy of the data. It's our way to provide high level availability and reliability of data. All the nodes that are synchronized between each other, and they automatically select a primary node. This is where the writes and the most of the synchronization happening. If primary fails, the MongoDB automatically fails over to another primary, and the nodes and the clusters selects next primary based on its own internal voting mechanisms. Applications connect to MongoDB via driver, and the driver and the replica set do lots of work in terms of synchronizing connectivity and ensuring data availability and reliability and consistency as well. So the driver needs to be aware of every single node within the replica set because the failover scenarios the driver is involved. MongoDB replica sets that are self-healing, they could be data center aware, and they provide workload isolation. If I have limitations where my scale goes beyond what my single node, my single server can do, we can use shared clusters. So shared clusters, they're essentially replica sets which each of them contains its own individual copy or portion of the data. Shared cluster is completely application transparent. It automatically scales and rebalances data in real time. And unlike many non-SQL systems, it doesn't just randomly sprays data across the shared cluster. MongoDB can actually control the policies and optimize query and placements of data across those shards. Within the shared cluster, there is a router called mongos, which is the small process which actually does all the magic in terms of executing queries on the distributed system. So it's important to note that mongos is a router, and the drivers in that case will connect to mongos as very, very in a similar way as they would connect to directly to a replica set. Obviously, in that case, drivers don't even need to know what are the shared clusters and their names. They just need to know the mongos connection strings. So the replica set provides high availability, and for horizontal scalability, we use sharding. So let's talk about MongoDB Data Platform. Back in 2009, MongoDB released core database that was a generally purpose database. Then 3 years ago, MongoDB added MongoDB Atlas, which was a fully managed cloud database, which allows users to take advantage of the versatility of MongoDB. Last year and this year, we announced general availability. We added Atlas Search. It allows organizations to perform very complex search queries against MongoDB Atlas database. So there is no need to spin up an additional search engine or move data back and forth. It's all built in. Last year, we also released beta of Atlas Data Lake, and this year it's going general availability this week. It allows users to easily query their cloud object stores, S3, for historical data, or use external data sources in a very natural way. All of those services, they all represented by a single document model and a single MongoDB query language. So it's consistent across all the data platform services. We also, over the years, provided a number of developer services. So things like SDKs and drivers, integration with IDEs and Compass, as well as ecosystem integrations like Kafka Connector and a suite of management tools, an Ops Manager and Operator. So if I run my application within cloud services, so I use one of the three most popular cloud providers, Windows, Azure, and Google, I would most likely now run my applications and services within Kubernetes cluster, whether I build it myself or will use one of the existing cloud provider services. So if I currently run my applications and services in one of the three major cloud providers, I would most likely going to use Kubernetes, whether it's deployed myself or use one of the provided Kubernetes services. In that case, there is no need to run MongoDB by yourself. You can use MongoDB data platform as a service, Atlas Data Lake, or Atlas Search. And in that case, those application services would directly connect to data platforms running in the same cloud. So there is no issues with connectivity or latency, it just runs pretty much in the same location. But it removes a lot of complexity from running those services, especially data services. So what do we use to run MongoDB data platform on-premise? And in particular, what is the best way to run MongoDB data platform on-premise? And over the last couple of years, we really came to a conclusion that it is a Kubernetes. So from our perspective, if our customers run application services on-premise in one of the Kubernetes distributions, like OpenShift or PKS or Diamante or straightforward Kubernetes upstream distribution, in that case, we are providing MongoDB private data platform. It is also built on top of Kubernetes, as we recognize that Kubernetes is the best platform to do so. This year, we are focusing on MongoDB core database and enterprise use cases, operating with most popular flavors of Kubernetes. So we're not only providing the best practices to run MongoDB as a service, but also we provide additional tools like Kubernetes Operator or Ops Manager running in Kubernetes. So if I'm application Kubernetes user and I want to develop my application and process some data, I really have two avenues at the moment. One is that if I run my applications in cloud and we use MongoDB Atlas, in that case, I have MongoDB Atlas Open Service Broker. With Atlas Open Service Broker, you are able to spin up and manage Atlas clusters directly from Kubernetes. You can control infrastructure provisioning, database setup, global distributions, and more. Compatible with Open Service Broker API, our broker will make MongoDB Atlas part of your Kubernetes service catalog and allow you to create clusters and manage directly Atlas servers directly from Kubernetes control plane. On the other side, if I run my application services on-premise, I can do so either in self-hosted Kubernetes distributions or infrastructures, which is usually fully isolated, or I have my own infrastructure, whether virtualized or bare metal, or even on my desktop. We offer MongoDB Enterprise Operator for Kubernetes, which is a native way, a native integration with Kubernetes for services and managing those services, together with MongoDB Ops Manager for Kubernetes, which provides an additional control plane to the operator and allows you to manage MongoDB in the day 2 type of operations and provides an additional control plane. So regardless of the way of deployment and management of those services, your application will consume the same document model and the same MongoDB query language, regardless of where the MongoDB is running. So a bit of a timeline. In 2008, we released MongoDB Enterprise Operator Preview. We were trying to understand, can we run MongoDB in Kubernetes? Was it ready? And also, was any of our customers interested? We've got a fantastic feedback from our customers with over 50 stations participating in our preview, as well as we've got some impressive results on MongoDB operations in Kubernetes. So in 2019, we released MongoDB Operator General Availability version 1, and we also released Atlas Open Service Broker. Only a couple of months ago, in this year, we released MongoDB Ops Manager, which is a Kubernetes distribution. So now we can deploy entire management and data platform stack inside the Kubernetes and get the benefits of Kubernetes of managing our own data platform. And this week, we announced MongoDB Community Operator. So this is a new project, which is fully open source Apache project, where we bring all the experience that we gain building enterprise operator back into the community, which will serve as a foundation for our operators and the MongoDB operators, whether it's a community or enterprise. So as a summary, what actually we've done up until now this week. So first of all, this week we're releasing MongoDB Ops Manager 4.4, which supports MongoDB 4.4 and all previous versions. Using our operator, we can deploy Ops Manager application server, which is the Java server. We can deploy AppDBs and all the backend databases required for it automatically. And also our operator can deploy all the required backup infrastructure to provide all the backup needs for your enterprise Ops managers. Around MongoDB service itself, the MongoDB Enterprise Custom Resource. We're releasing every 3 weeks, so there is every 3 weeks there is some new feature being added. I would like to highlight what we've done over the last couple of months. One is that we opened up pretty much all MongoDB advanced configuration options to CRD, so we can fine-tune write cache or enable encryption at rest directly from Kubernetes APIs. We also improved how we manage stateful sets and how we expose stateful sets to the YAML files and CRDs. And we also this week we announced Community Operator. This is an open source project, Apache v2. So everybody welcome to participate and help us out figuring out what's the next features we need to build. At the moment, it can deploy a replica set and do an upgrade from one version to another. We are going to work over the next couple of months and add new features like enabling TLS authentication and user management, monitoring and things like that. But we are looking for your feedback to determine what we need to build next. So now it's time to move into MongoDB in Kubernetes architecture and look at kind of have an inside view of how to actually build MongoDB persistent services inside Kubernetes. So one important point is that we have MongoDB Enterprise Kubernetes Operator, and this operator will manage 3 new Kubernetes resources. So those resources, they're high-level abstractions that we register with Kubernetes, and operator takes care of managing those resources. One resource is MongoDB, which is obviously our server. It could be standalone, replica set, or shared cluster. So it represents one of those 3 clusters. Another resource is MongoDB user. This allows us to create MongoDB users and create them inside the clusters from Kubernetes API, directly Kubernetes native way. And also a new resource that we added recently, which is the Ops Manager. So Ops Manager is this additional control plane that will help you, enable you to manage MongoDB Enterprise, do backups, provide advanced monitoring, analytics of MongoDB, do profiling, index analysis, and much, much, much more. So if we look at the diagram, so here we have a Kubernetes cluster and one namespace where we have our operator, which deploys Ops Manager application. So this namespace is isolated management namespace where we have this management tool running. Now we have our namespace where we'd like to deploy our Kubernetes cluster, or our MongoDB cluster. Most likely that's where application is going to be as well. So first thing we'll do, we'll deploy our operator. An operator needs to have access to config map and the secret. Config map just holds the connection string to Ops Manager and a couple of properties as well. And secret obviously holds the API key so that operator can connect to Ops Manager. Once this is up and running, we can start deploying MongoDB services. One is apply MongoDB CRD, which declares what kind of cluster operator needs to provision. as well as a number of CRDs that represent MongoDB users. Typically, we would deploy multiple CRDs. One will be, let's say, admin user that have full access to database. One would be the application user, let's say it's represented by X509 certificate or Scrum SHA. We often see users being mixed with different authentication types. So one admin user would most likely going to be an LDAP user, which is an actual human. And another user will be an application, which is X509, let's say authentication or Scrum SHA username and password, because that's kind of easier to manage and rotate those certificates with some kind of external systems. Obviously, Operator, by building MongoDB resources, are going to use very standard Kubernetes resources like stateful sets, persistent volumes, services, secrets, storage classes. We're not inventing anything new in Kubernetes. We use very standard Kubernetes resources, and Operator just manages a collection of them, put them together into a service which delivers your MongoDB cluster. So here's an example. I kind of feel it's always important to show what does the actual CRD looks like in real life. So here's the example on very basic MongoDB deployment. So in this case, we have a kind MongoDB. So this will indicate Kubernetes to inform our operator that this is a new request to create that particular resource. We define how many members our replica set will have, what kind of version we need to deploy. A link to Ops Manager, so operator can actually deploy, connect to Ops Manager and use Ops Manager to configure and manage that cluster. We obviously say that persistent is true. Some cases, when you're a developer, you don't maybe want to persist your very fast deployed MongoDB forever. So you could choose false, but generally persistence will be true. And then the pod specs, a very standard Kubernetes way of declaring parameters and specification of your services. We would always typically declare how much CPU limits and requests and memory requests we need, so that our Kubernetes can track and enable quality of service guarantees. And also we declare what kind of persistence, how much disk we need. In that case, it's a single storage with 10 gigabytes. So if we look at what is actually Operator get deployed and how does it look inside. So first of all, when the CRD is applied, Operator goes and starts provisioning Kubernetes resources. First thing it's going to do, it's going to create persistent volume claims, which then Kubernetes is going to serve with persistent volumes out of the declared storage class. Once the persistent volume claims receive their persistent volumes, Operator is going to create a stateful set. So stateful set is like special pod, right? That has special rules, and it's completely independent from persistent volumes. So my pods and my volumes are going to be completely different lifecycle. So the stateful set is essentially a pod. In our replica set with 3 members, we're going to end up with 3 stateful sets pods. And those pods will be then fronted or exposed on the network using the service, which Operator creates. The interesting note here is that the Kubernetes service will automatically create a SRV record, which you can use MongoDB connection string with. So in that case, if we scale our replica set to, let's say, 5 members, Kubernetes will automatically change the DNS in the service, and the CRV record will change automatically. And then our drivers and MongoDB connection string doesn't need to track names of individual pods. It just needs to know the name of the service, which makes the connectivity so much better. So here's our Kubernetes cluster, maybe a different look at how things work. Kubernetes cluster with different nodes. So let's look at the deployment. So we have our different nodes, which are our worker nodes, and our namespace that is kind of a virtual entity that usually available across all the worker nodes. So we deploy our Operator, which Kubernetes could place on any random node. Operator is a very small container. It doesn't need much resources at all. It runs on a minimal image. And then Operator will deploy CRD, in this case, 3 replica set, and Kubernetes is going to place those stateful sets and pods and volumes according to the label selectors, node affinity and pod affinity rules. So in that case, it just chose those worker nodes to place those pods. Let's say we want to deploy another MongoDB cluster. In that case, we would recommend to use another namespace, so those clusters are kind of isolated from role-based access permissions. And we deploy a new CRD that has a 5-node replica set. In that case, the operator may deploy in some other worker node, but typically Kubernetes will try to distribute stateful sets across different worker nodes. And if there are enough resources, could actually collocate them. And that's where the definition of how much memory and CPU is required is important, because Kubernetes will proactively make decisions of where each of those pods should be placed, if there is enough resources on each of the workers. And then if the workers start to consume more and more resources, I can actually reallocate those workloads across the cluster. So let's look at MongoDB Community and MongoDB Community Operator, what we actually are releasing this week. So this is how it looks, the same 3-node replica set. And what you would probably notice that it looks very, very similar to our enterprise solution. It's the same 3 nodes backed by a persistent volume claim, and the operator manages this high-level abstraction and creates all the necessary Kubernetes resources. The difference really comes from inside of each individual pod and how it's been deployed. So if we look inside our stateful set pod, what we do have here is 2 containers running inside a single pod. One container could be any image that has MongoDB installed. So it could be our most popular Docker image, could be any image that you decide to build for your own organizations because you need very specific requirements on, let's say, security libraries or security fixes. And the second container is the sidecar, which runs our MongoDB agent. So for people, if you're not familiar with our enterprise solution, we have MongoDB agent that provides an additional management capabilities to MongoDB clusters. And this is what we've done. We released MongoDB agent for everybody for free to use license. So anybody can use within community our enterprise agent. And what it does, it provides an advanced management capabilities for our Kubernetes operator. MongoDB agent constantly monitors MongoDB processes for its stability, and provides an additional guarantees that the cluster is operational. MongoDB agent also provides readiness and liveliness probes for the pod. So if we consider standard health check on the pod will be, does my process running? MongoDB agent will do a couple of dozen verifications of not only MongoDB, but the MongoDB cluster itself, and will make sure that it's running. It will try to correct majority of issues, and it's a CAN. It will provide the readiness and liveliness probes information, and then will let operator and Kubernetes to deal with errors. So what we provide with our MongoDB agent is this multi-layered system of making sure that MongoDB runs and is healthy. So wait, what about Ops Manager? We haven't talked about how Ops Manager looks like inside Kubernetes. And the reason I haven't discussed Ops Manager yet is because I really want to talk about community first. So Ops Manager is the normal web application. It's a Java app, right? It needs pods with HTTP web servers, but also need database. But obviously, to deploy MongoDB database, we need Ops Manager, and Ops Manager needs MongoDB, which is chicken-leg problem. And that's where we use very similar technology to our community operator, where if the CRDs, Ops Manager CRD is applied to my cluster, operator will start to deploy as enterprise MongoDB replica set. And it will use very similar technology that what we actually releasing now with the community operator. It actually doesn't need Ops Manager at this stage to launch a very standard replica set for the Ops Manager itself. And once this replica set is up and healthy, we deploy Ops Manager pods, which is normal stateful set deployment. So Ops Manager is a Java app. We can typically deploy multiple instances for HA, and it works as any other normal Java app. One probably note to make is that Ops Manager, traditionally, majority of Ops Manager deployments will be happening in air-gapped environment. So Ops Manager has this functionality of managing MongoDB installers offline, kind of working as the repository for MongoDB installers. In Ops Manager 4.4, we released new option to pick up those MongoDB installs from any web server, like S3 store. So if you have your own S3 server locally, instead of placing MongoDB installers inside the Ops Manager disks, you can now upload them to S3 and point Ops Manager to that URL. So for more demos, please visit our technical talk called Runtime Kubernetes, Community and Enterprise MongoDB in Containers by Louis. And also, we have a number of demos in our private cloud booth. It's a virtual booth. They can go anytime there and look at the demos and presentations. It's not only talks about Kubernetes, but also about Ops Manager. So it has quite a few videos. Few words about Atlas Open Service Broker. So if we talk about architecture of Atlas Open Service Broker, first of all, Atlas Open Service Broker implements Open Service Broker API, which is the well-recognized open standard for providing services. So first of all, we deploy Atlas Service Broker in Kubernetes, which then integrates with Kubernetes Service Catalog. Our clients would use the Open Service Broker API or the Catalog API to look at what services are available and request provisioning of the service. So once the provisioning is requested from a service catalog, Atlas Open Service Broker goes to Atlas and requests a server MongoDB cluster to be created and provisioned. Once it's provisioned, there is a representation in the catalog of that instance of MongoDB Atlas. Application or could request a binding from Atlas Open Service Broker. So binding is essentially a way of connecting application with a service, and in our case, it means creating a user. So when the application makes a binding request to Atlas Open Service Broker, it creates a user in MongoDB Atlas database, and then application will get that user's credentials and connection string. So what that means is that when we have our CI/CD for the application, we can use very standard Kubernetes interfaces to create MongoDB clusters that this application needs, but also create credentials and connection strings automatically from Kubernetes. There is no need to jump into Atlas UI and request the clusters or copy-paste URLs. So Atlas allows us to have a very native integration with Kubernetes, very, very similar to majority of many other services available in Kubernetes catalog, making your experience completely Kubernetes native. So now let's look at best practices running MongoDB in Kubernetes. First of all, define a configure persistence. With our MongoDB CRD, we can either define single mounting points for this kind of simple, very quick clusters, MongoDB clusters, or we can declare multiple mounting points for data, journal, and logs. We can define what kind of volumes Kubernetes will deliver based on just storage requirements. We can also define label selectors for storage classes, so to let Kubernetes find the best suitable storage class based on the labels. Or we can directly pick particular storage class and target particular storage class for that particular volume. This allows us to kind of parallelize the I/O and the disk requests between multiple volumes and maybe even the multiple devices. So optimizing MongoDB write and read performance. Split horizon. So we discussed at the very beginning that how replica set has multiple nodes, and the drivers need to be able to connect to each of the nodes in case nodes fail over or change their primary. So what's important that the application, the user and the driver needs to be able to talk to any of the nodes in the replica set. So we have an additional configuration called replica set horizon, where we can define what are the horizons or DNS namespaces, if you like, MongoDB can be accessed from. So we can specify one horizon of all my externally exposed MongoDB nodes, and my horizon number 2 will actually declare all the names of my node replica set nodes of how they actually called and referred to internally inside Kubernetes cluster. So when the driver makes a request to MongoDB server, it actually discovers from the right horizon. It doesn't get the mix of internal and external names. So dealing with namespaces. There's lots of ways how we can map MongoDB service and Ops Manager representation and Kubernetes representation of that service. Typically what we say is keep it simple. We'll keep single instance of Ops Manager for all MongoDBs in your infrastructure. One operator per Kubernetes namespace. We do recommend to deploy Kubernetes for each separate operator for each namespace, It simplifies operations of this and kind of separates which namespace and how do you manage those processes. We could deploy operator cluster-wide, but there is only very few cases when it's kind of that makes sense. Kubernetes namespaces map really well to Ops Manager organizations. Ops Manager organization is this isolated tenant idea which maps really well to namespaces. And in that case, MongoDB cluster equals Ops Manager project inside this organization. Because MongoDB cluster within Kubernetes, MongoDB CRD, has its own set of permissions, controls, the same way as the Ops Manager project. But we typically like customers to use one config per MongoDB cluster CRD. We can kind of share config maps across multiple clusters, but it actually makes it much more complicated 3 months down the line where we'd like to move one cluster or remove one cluster, and that makes it kind of confusing. Well, can I remove this config map? If we have one-to-one mapping config map secret MongoDB cluster, it makes it very easy to maintain and going forward. Always specify resource requirements in terms of CPU limits and CPU requests. You can use our high-level abstraction within our pod spec called CPU request, memory, and memory requests. But if you don't specify one of those requests, the Kubernetes will downgrade quality of service guarantees on the cluster, and your MongoDB will not perform as effectively. The memory requirements requests are super important for MongoDB wire cache, because without memory requests, it's going to grab all your memory. It will consider it has access to all the memory within the working node, and will just grab half of it for the wire target cache. If you specify memory requests to the limit, to the extent that you think you need it for MongoDB cluster, wire target cache will be sized appropriately. You can always scale it up and down later if you see that, let's say, you don't have that much of a traffic going in, or you need much more capacity. In that case, you just increase memory requests, and Kubernetes will deal with allocation of new resources. Use multiple availability zones. Kubernetes, it's a good idea to deploy Kubernetes cluster across multiple availability zones, and we can use node affinity and pod affinity, classical and Kubernetes definitions. It's a good idea for Kubernetes clusters to deploy across multiple availability zones. So if the one zone goes down, the Kubernetes cluster will maintain working. We can accept definitions of pod affinity and node affinity to make sure that Kubernetes deploy MongoDB nodes across those availability zones. We use very standard Kubernetes definitions. It's very well documented in how Kubernetes deploys with label selectors and node affinity and pod affinity rules, policies. It's very similar to any other application that you would like to run reliably within the infrastructure. So use labels and node selectors. Side note on Kubernetes federation. It always comes up, especially in the last couple of months, of our customers will looking to deploy MongoDB cluster across multiple Kubernetes clusters. So the MongoDB cluster could span multiple Kubernetes clusters, whether they are across different regions or parts of the world or different kind of failure domains. So one note, you could run MongoDB across multiple availability zones, but it must be within the same Kubernetes cluster. So in fact, it's always a good idea to run Kubernetes across multiple availability zones, and MongoDB Operator can work with Kubernetes to ensure that stateful sets are deployed across those availability zones using a node affinity and pod affinity. We cannot run across multiple Kubernetes clusters at the moment. This is something that we are currently investigating and trying to make a design. We are looking very close at Kubernetes Federation's special interest group. It is still in early days for federation. It's still an alpha, work in progress. And on the roadmap we have, but regardless of the progress with Kubernetes Federation, we have on a roadmap to find a solution and do a POC. So collocate, another kind of important aspect. For shared clusters, MongoS is this routers that route requests across different shards. We generally recommend collocating MongoSs together with application pods. And just a reminder, you can use labels to collocate them. So we can put match expressions on the MongoS pod spec to ensure that it gets placed on the same worker node as your application, reducing that traffic, basically making it local. Multitenancy you can manage with labels, so we can make sure that anti-affinity and affinity rules, playing with anti-affinity and anti-affinity rules and node selected terms can help us to ensure that, let's say, MongoDB clusters are not placed with clusters of different customers or different parts of my product or organization, and there is to kind of ensure the segregation that is happening. So labels really here is the key to do majority of policy definitions about how and where the MongoDB pods are placed. Always enable TLS. It is our standard secure configuration that every MongoDB cluster has TLS enabled. It's as easy as adding security TLS enabled to true and giving us few certificates. One reminder is that you can use Cert Manager, which is the independent project that manages a variety of different certificate providers for you in Kubernetes. So you can use Cert Manager to generate certificates that MongoDB cluster needs, and then we can pass them on to our CRD, and then we'll take them off and distribute them in the right places. Previously, we could generate our certificate ourselves with our operator using Kubernetes sign-in authority. But what we recently discovered is that in some versions of Kubernetes and some distributions of Kubernetes, that functionality isn't working. So if it does work for your cluster, if you configure it to run in your cluster so that Kubernetes sign-in authority API distributes all the certificates across all the nodes properly, you can use it. But going forward, we see quite a big adoption of Cert Manager, and that's where we would like to go going forward. Always enable authentication. Authentication just guarantees that nobody can access your cluster without permission. It's also as simple as adding another couple of lines to your TLS certificate configuration, authentication enable true, and picking which mode of the authentication you would like to get. Most basic one is a Scrum. For the enterprise, most likely you would use LDAP and X509. You can mix and match those modes. LDAP is still work in progress. We've just released a couple of new features, but we'll over the next 3 to 6 weeks, LDAP support will come 100%. We'll definitely generally see that customers would configure LDAP and X509 mode, authentication modes, where the administrators will use LDAP to connect to MongoDB server, where applications will be connected to X509 certificates with its own rotation policies and kind of managed in their CI/CD and security policy guidelines separate to LDAP. Obviously, you can mix and match, but always do choose at least Scrum SHA. And actually, with Kubernetes, X509 is very easy. Generating those certs is quite straightforward. So give it a go, X509. You will get much better secure clusters. So in summary, use labels and selectors. They will get you a long way in terms of how the resources are placed and balanced. Always enable authentication and TLS, and configure resources and persistence to ensure that you have enough storage and Kubernetes quality of service is delivering the resources that you need for the optimal MongoDB performance. Now it's time to discuss our roadmap for 2020. I'm a PM. I kind of like this kind of conversation. In Q2, we will continue to spend time with our community operator. We would like to get to a stage where it can deploy fully secure, authenticated MongoDB community replica set. Enterprise operators will see more enterprise features, like LDAP will be ready in a few weeks. MongoDB backup will be next, as well as encryption at rest. All those features are currently configurable in Ops Manager. However, we would like to enable those configurations in Kubernetes native way. In Q3, Community Operator will continue to be our focus. Our plan is to look at sharded clusters and backups. However, I hope for the community support here with the feedback and pull requests. So I'm sure our roadmap will change. Enterprise Operator. We will start MongoDB multi-cluster POC in Q3. Our goal is to figure it out how to deploy a truly global MongoDB cluster that spawns across multiple Kubernetes deployments. At the same time, we can maintain similar operational benefits with the operator framework. We will continue to focus on the autonomous operations, as Operator Hub calls it, autopilot. We already provide many features here, like automatic failover, data rebalancing, and reconfiguration. However, sky is the limit here. Auto-scaling, persistent volume resizing, and performance optimization is just one of the few areas we can look at. In conclusion, we have 3 resources to rule them all. One is the MongoDB, which represents MongoDB services clusters, the standalone replica sets or sharded clusters. MongoDB user, that represents users that need to connect to those clusters. And Ops Manager, that provides additional control plane for MongoDB clusters running in enterprise. I hope you found this talk interesting. Thank you very much for your time, and good luck.